Deep under the ruins of Chernobyl's Reactor 4 sits a lump of material so unusual that, according to a widely repeated account, engineers once tried to break off a sample using an AK-47 with armor-piercing rounds. Not because it was dangerous to touch, though it was, but because it behaved less like debris and more like a single stubborn rock. At first, it's tempting to imagine a nuclear accident as an explosion followed by a fire, then cleanup. But Chernobyl's most important damage happened in a slower, heavier way. After the April 26, 1986 disaster, parts of the reactor core didn't just burn. They melted, mixed with surrounding building materials, and moved. The central question is simple. How does something that began as fuel pellets and metal turn into a stone-like mass that could flow through corridors and become so difficult to even sample? The key term is corium, a lava-like mixture created when nuclear fuel, cladding, and structural materials melt together. In Chernobyl's RBMK reactor, that melt included uranium fuel, zirconium from fuel cladding, steel, and large amounts of sand, boron, lead, and dolomite dropped in by helicopters during the response. When corium forms, it doesn't stay politely inside the reactor vessel. It seeks the lowest point, like any hot, dense fluid, and it reacts with what it touches. That matters because below Reactor 4 was concrete, lots of it. Hot corium attacks concrete chemically and physically, releasing steam and gases while eating downward. In the months after the accident, responders feared the melt could reach water in lower levels and increase contamination. This is why so much effort went into draining areas and building barriers, and why thousands of workers were sent into hot, cramped spaces with strict time limits. The problem wasn't only radiation, it was the uncertainty of where the melt would go next. By late 1986, teams exploring the lower rooms found several hardened corium formations. The most famous was in a steam distribution corridor, where it pooled into a rippled shape that reminded observers of an elephant's foot. Early radiation readings near it were extreme, often described in the thousands of roentgens per hour at close range, meaning a person could only be nearby briefly, even with protection. Robots were tried in parts of the site, but intense radiation and debris made remote work unreliable. This is where the sampling problem shows up. Engineers needed physical samples to understand what the material actually was, how much fuel it contained, how it cooled, and how it might behave over time. But the mass was hard, irregular, and in a place where setting up drilling equipment was difficult. The famous AK-47 story appears in multiple retellings, firing armor-piercing rounds to chip off fragments when other tools were impractical. Details vary by source, but the underlying point is consistent. Getting a small, representative piece was less like scooping ash and more like quarrying ceramic. Here's the clearer aha behind the legend. The elephant's foot wasn't unstoppable because it was mysterious. It was unstoppable because it followed ordinary physics under extraordinary conditions. Chernobyl's core melt became a dense, ceramic-like composite as it cooled, part fuel, part concrete, part metal oxides, locking itself into a single mass. While it was hot, it could creep and flow, pushed by gravity and driven by chemical reactions with concrete. Once it cooled, it became mechanically tough, chemically complex, and dangerously radioactive, making simple tasks like drilling or sawing far more complicated than they sound. The implications go well beyond Chernobyl. Corium research reshaped severe accident planning, how to keep molten fuel inside containment, how to manage hydrogen, and how to design core catches or sacrificial concrete layers in some newer reactor designs. It also changed how engineers think about cleanup as a long system, not an event, tracking radiation fields, building shielding, monitoring dust, and planning for decades of slow change. The 2016 new Safe Confinement over Reactor 4 reflects that mindset. Control the environment first, then work. So the strange part isn't that someone may have fired bullets at a radioactive rock. The strange part is that a nuclear reactor can turn into something rock-like at all, and that understanding it requires geology, chemistry, and infrastructure thinking, not just nuclear physics. If you'd like more calm explanations of how complex systems behave under stress, consider subscribing to Quietly Explained.